Okay, let's continue with the remaining 6 examples in this section. The next example says, use an identity to write the following expression: 2 sine of 22.5 degrees cosine of 22.5 degrees as a single number. Right? So they don't want you to just punch this in the calculator and get an answer. Basically, they want you to do this, find the exact value. Okay, don't use the calculator. Well, you should know from everything we've done in this course that sine of 22.5 degrees and cosine of 22.5 degrees, we don't know how to do unless we use a calculator, okay? So I don't know anything about 22.5 degrees, so I can't find sine and cosine of it. However, if you look at this expression, it should remind you of something. It looks just like the right-hand side of the double angle formula for sine 2a, right? 2 sine 22.5, cosine 20.5 degrees. It looks just like this. Since we can't do anything with this in its current form, what do? We know this is equal to this, so let's rewrite this in that form. That's what all the examples were on the previous page that we just practiced with, right? Rewriting from one form to another. In this form, I can't do anything. Let's rewrite it in that form. Okay, so if you have something that looks like 2 sine of an angle cosine of an angle, that's equal to sine of double the angle. So this is the sine of double 22.5, which is 45 degrees. And we do know how to handle 45 degrees because that's one of the angles in one of our special triangles. Okay, so sine of 45 degrees, okay, 45 degrees, right, is here. That's your 1, 1 square root of 2 triangle. And sine is opposite over hypotenuse. And there's your answer. Again, I'm not rationalizing. Okay, be aware that a computer package or the back of the book is going to rationalize. Multiply by root 2 over root 2. Okay, so that's the idea of these identities. Something you have in a certain form you can't deal with. So what do? Rewrite it using the identities in the other form. And sometimes you go from left to right, sometimes you go right to left. It depends on what you have and what you're trying to find. Now the next example is similar, right? It says rewrite this, use an identity to write this expression as a single number. Now first of all, I mean pi over 8 is written that's in radians. Again, not because there's a pi, because there's no degree sign. That's how you know an angle's in radians, because there's no degree sign. Okay, now it's pi over 8, an angle in a special triangle. Well, it's easy to recognize angles you can do with a special triangle where in radian measure. If you have a pi and a fraction that's reduced, like we have here 1/8, okay? If the denominator is 1 or 2 or 3 or 6 or 4, it's either an angle in a special triangle or it's a quadrantal angle, and you can do those without the calculator, okay? So if you have a pi over 1 pi, 2 pi, 6 pi, negative 5 pi, or if you have pi over 2, 11 pi over 2, 71 pi over 2, the denominator is 2, so that's a quadrantal. Pi over 3, pi over 6, pi over 4, those, 7 pi over 4, 8 pi over 3. All of those you can do with special triangles because the denominators are 1, 2, 3, 4, or 6. Now this is a 1/8 pi, so this is not one of the ones in the special triangle. So just like this, you can't do this. But what does this remind you of? I can't do anything with this because this is neither a quadrantal nor an angle in a special triangle. But what does it look like? It sort of looks like this one, not quite. Okay? Remember when we had expressions like 1 minus sine squared theta, and it was 2 items of the 3 in your Pythagorean identity, and we made a new identity from the Pythagorean identity? We're going to do the same thing here, right? So let me write down the identity that this reminds me of. So it looks like cosine 2a is 2 cosine squared a minus 1. Now this is an identity we know. This doesn't quite look like that, but what could you do to this identity to make the right-hand side look like that? If I multiply both sides of this identity by 1/2, half of 2 cosine squared a is cosine squared a, and then half of negative 1 is negative 1. So I played the same game that I played before with those Pythagorean identities. With the Pythagorean identities, we subtracted stuff from both sides. Here I'm multiplying both sides by a number. Okay? So if you have an identity that you already know, you can do things to both sides to make a new identity. So if you multiply both sides by 1/2, now I've made a new identity from the old one, and this right-hand side matches that. Now be careful, you cannot take the half inside the cosine and cancel the 2, okay? Your trig functions don't work that way. All right? So now this looks like this. This form is not helping me because of the pi over 8, but this is equal to this. So that should be 1/2 cosine of whatever angle's there, double the angle goes here. Double pi over 8 is pi over 4, which we know we can do with the special triangle. Okay? Okay? So the key with here is I can't do anything with this because I don't know the angle pi over 8. It's not a special triangle quadrantal. But this expression looks like this one. So I wrote down the identity that side, the right-hand side, looked like. To make this side match that, I multiplied both sides by 1/2. Now this expression matches this one. This is equal to this, so I rewrote this to that, going from here to here. And now, pi over 4 is 45 degrees. It's the same triangle here. Cosine is adjacent over hypotenuse. So cosine of 45 is 1 over root 2. And there we go. Right, so sometimes you have to take an identity you know and do something to both sides to make a new identity that's useful. This didn't match that, so I made it match. Okay, now the next one says, suppose that cosine theta is minus 12/13 and sine theta is positive. Okay, that's a lot of information about theta. The instructions say find sine of 2 theta and cosine of 2 theta. Okay, so I'm trying to find sine of 2 theta, and I want to find cosine of 2 theta. Okay, so I want to know something about the angle 2 theta. I want to know something about the angle 2 theta. Right, this is not a trick question. What did the original information in the problem tell me about the angle 2 theta? Nothing, right? They told me cosine theta and told me something about sine theta. The information they gave me was about theta, and we want to know about 2 theta. Boy, I wish we had something that related information about theta to information about 2 theta. That's exactly what this section's all about, right? Here's information about a single angle, A. Here's information about the double angle. Single angle, double angle, single angle, double angle, okay? So they told us a lot about the single angle theta, and they want to know about the double angle. Well, obviously, to find sine of 2 theta, since I know nothing about 2 theta, let's rewrite sine of 2 theta in terms of thetas. This is going to be, let me put it over here, 2 sine theta cosine theta. That's the identity, okay? It's the same strategy that I did here. I didn't know anything about that, so I rewrote it in terms of the double angle. Here, I want to know about the double angle, and I know nothing, so I wrote it in terms of the single angle, right? You can go both directions. Okay, so let's just focus on this one. We'll come to the cosine in a minute, right? So to do this, to fill this out, I need to know sine theta and cosine theta. Well, they told me cosine theta was minus 12/13, so we already know that, right? Now, don't put negative 12/13 for theta, right? Don't say cosine minus 12/13. No. I don't know theta in this problem. Cosine theta is minus 12/13. So instead of cosine theta, replace that whole thing with minus 12/13. Now, we need to know sine theta, which was not given. I know sine theta is positive, so there's a positive number that goes here. But what can we do? This is enough information to sketch a picture of angle theta. All right, let's draw a triangle here. Well, where are we? Cosine is negative and sine is positive. So with those two conditions, cosine is negative and sine is positive, in which quadrant would theta have to be in? The terminal side. Clearly it's not the first, because cosine's negative and every trig function's positive in the first. Right? So what quadrant is this? This is in the second quadrant, isn't it? Now I don't know that's a rotation, I just like to put something out. Okay, so sine is positive in the second quadrant and cosine is negative. Well, let's use these numbers to label two sides of the triangle. Cosine's adjacent over hypotenuse. Now, when I say adjacent, it's not adjacent to theta, it's adjacent to the reference angle for theta. So the adjacent and the hypotenuse. And remember, when you have a fraction with the negative can go on the numerator or the denominator or out front. So just because I wrote it with the 12 doesn't mean it's with the 12, but it is, right? Because the hypotenuse, the r is always positive here. Now, how do we find the other side? Well, just use Pythagorean theorem. This is one that shows up all the time in a trig course. A triangle with hypotenuse 13 and leg 12, the other leg is 5. You can work it out with Pythagorean theorem. I just won't waste the time here. So 12 squared plus y squared is 13 squared. Solve for y, you'll get a 5. But 5, 12, 13 is a common Pythagorean triple, as it's called. 3, 4, 5 is another one, right? A 3, a 4, and a 5 on the hypotenuse. So you might just want to memorize those because they show up all the time. Now, there's a picture of theta. You could do all 6 trig functions, but here we only need sine. Sine is opposite over hypotenuse. That's 5 over 13. And if we multiply, again, think of the 2 as 2 over 1. 2 times 5 times negative 12, that's 10 times negative 12, or negative 120. And 13 times 13 is 169. So there's the sine of 2 theta. Now we need to do the same thing for cosine 2 theta. Now the double angle formulas for cosine, there are 3 of them, right? So this is what I'm trying to find, but I don't know anything about 2 theta. So we want to write it in terms of theta, which we now know a lot about. And you can pick any one you want. You can pick any one you want. But remember the difference. This one has cosine squared and sine squared. This one just has cosine squared. This one just has sine squared. Now we have a picture for theta. Right? So we could fill in all of these if we want, okay? It doesn't matter which one. However, let's pretend that we hadn't done the sine 2 theta part. Pretend we hadn't done anything. Suppose you were given this information and it said find cosine of 2 theta. Well, which is the easiest of the 3 to use? They gave us cosine theta, so it would be easiest just to use this one. Then you don't have to find sine. Now, we already have the picture, so it doesn't really matter, okay? But if we hadn't done this work at all, my point is we could have done cosine 2 theta first without having the picture. So I'm just going to use this one just because we already know cosine theta. So cosine 2 theta here is 2 cosine squared theta minus 1. Okay, I'm just recopying the formula here. All right. So cosine theta squared minus 1. But they told me cosine theta was negative 12 thirteenths, right? So there's no triangle. You don't have to draw a triangle picture to finish this one if you choose this formula. If you chose the first one or the third one, you'd have to go to the picture to get the sine of theta as 5/13. And now it's just a matter of doing some arithmetic. Negative 12 thirteenths squared, that's 144 over 169 minus 1. And think of the 2 as 2 over 1, so when you multiply fractions, you get 288 over 169. And to get a common denominator, you need a 169, so that's 169 over 169, because that's 1. And then 288 minus 169 is, what is that, 119? Okay, so the sine of 2 theta is minus 120 over 169, and the cosine of 2 theta is 119 over 169. Now, from this information, we can determine in which quadrant 2 theta is, can't we? Right? Now, you can't just say, oh, theta's in the second, so 2 theta is in the fourth, 2 times the second quadrant. It doesn't work that way. Right? But where is sine negative and cosine positive? Well, that actually is the fourth quadrant. So I know 2 theta's in the fourth quadrant. Now, if I just had this piece of information without this one, sine 2 theta would either be third or fourth. I wouldn't know which one. But with the cosine theta is positive, I know 2 theta's in the fourth. But be careful, right? Just to show you can't just say, oh, double the second quadrant's the fourth. I mean, if theta were 10 degrees, for example, 2 theta would be 20 degrees. So theta's in the first quadrant and 2 theta's in the first quadrant, okay? If theta is 80 degrees, theta's in the first quadrant, but then 2 theta would be 160 degrees in the second quadrant. So you really have to work stuff out to see where things are. Okay, the next 2 examples are identities we want to prove. Okay, so I'll just start here. So it says verify sine x plus cosine x squared is 1 plus sine 2x. Right? And show this as an identity. Okay, so what's the procedure for showing an equation as an identity? You start on one side and work your way to the other. Now, I mentioned before in previous lectures that something I look for is which side is more complicated. Again, whatever that means. You can argue the left-hand side here is very complicated because it's a bunch of stuff squared. So that's complicated. But on the other hand, you can argue the right-hand side is more complicated than the left if you look at the angle, right? The angle over here is x and x. The angle over here is 2x. This angle is more complicated than the angle over there. Sometimes using that argument for more complicated is useful. But remember, when you're choosing which side to work with, to start with, another factor is, do you have an idea of what to try first? Okay, so I do have an idea for each side, right? Here, you have a bunch of stuff squared. I think I would just square it. And over here, I have 1 plus sine 2x. Notice I have 2x, the double angle here. I have the single angle here, so it would make sense to use the double angle identity to go from doubles to singles. So I actually do have an idea on both sides. I'm just going to start with the left. All right, so write down the side you're starting with so the reader knows which side you're starting with. Now you have to FOIL this out. You can't do sine squared plus cosine squared. That's not how you do that, right? Right over here, let me write this out. That's sine x plus cosine x times sine x plus cosine x. You have to FOIL that mess out. So sine x times sine x is sine squared x. You get a cosine x sine x here. And then you get a sine x cosine x here. And then you get a plus cosine squared x. Sine squared plus cosine x sine x plus sine x cosine x plus cosine x squared. Okay? Have any idea what to do next? Well, one thing there are two things here you might have noticed. First of all, these two are exactly the same, right? Cosine x sine x and sine x cosine x are the same thing. So you can combine those. So why don't I do that in one step? Okay, so that's what you get. Just add those two together. You get two of them. And then what? Well, something else that you may have noticed here. Sine squared x plus cosine squared x is 1. That's one of your Pythagorean identities. So you've got to keep those in mind because they just pop up here and there, and you need to know them. And be careful. Sometimes, notice the sine squared and the cosine squared are not next to each other. But sine squared plus cosine squared x is 1. So this is 1 plus 2 sine x cosine x. And then what? Well, every once in a while, look and see what you're trying to get to. I'm trying to get to 1 plus sine 2x. There's a 1 right there. We've got our 1. So if you didn't notice the Pythagorean identity here, if you look and see you're trying to get a 1, you say, well, how am I going to get a 1 out of this? And then you might have noticed that those are add up to 1. Now what about 2 sine x cosine x? Well, that's one of your identities right here. 2 sine x cosine x is sine 2x. Oops. 2 sine x cosine x is sine 2x. And that's what we were trying to get to. So notice if we'd started with the right-hand side, my suggestion was to rewrite this in terms of x's, which is what I would have done. Now, the problem here is it's not obvious to rewrite 1 as sine squared x plus cosine squared x. That's not obvious at all. It's so simple, you don't know what to do to make it more complicated. So if we had started with this side, we probably would have gotten stuck here, and I probably would have come back to here anyway. But notice here, it got so complicated to start with, then it's just a matter of simplifying. Here, this is so simple, how would you know to rewrite that as sine squared x plus cosine squared x? Okay, the next one is another identity. It says sine of 4x is 4 sine x cosine 2x. Wow. Verify this is an identity. Oh gosh. Okay, so same argument as before. Which side do we want to start on? You could argue the right-hand side is more complicated because there's a lot of stuff going on. But notice the angles on the right are x, x, and 2x. The angle on the left is 4x. So the left-hand side, the angle is much more complicated than the angle on the right. So just for variety, I'm going to start on the left. Instead of doing the more complicated expression, I'm going to do the more complicated angle. So write down the side you're starting with, sine 4x. I'm starting on the left on this problem. Okay? Now, my thinking here is, this angle is 4x, and the angles over here are x, x, and 2x. I've got to make the angles simpler. Well, how can you do that? Right? Double angles to single angles make the angle smaller, right? Double to singles, doubles to singles. So, what we talked about in the first half of this section, how do you go from the double angle to the single? It doesn't have to be a 2, it's just whatever angle is here, half of it goes in each place there. So sine of 4x is 2 sine 2x cosine 2x, right? Whatever angle's here, my 4x, half goes here and half goes here. So I've reduced my 4x's to 2x's. So sine of 4x is equal to this. And again, let's look and see what we're trying to get to. I have this, I'm trying to get to here. So you don't want to touch the cosine 2x. I need a cosine 2x at the end, and I have it. So you might be tempted to, cosine 2x, let's use one of these to go to x's, but I don't need to, well, you need to go to x's here, but you need this cosine 2x, so you don't want to ruin that. If you split that, if you break that down into the x's, you're going to lose that. So you don't want to mess with that. So it looks like the only thing left to mess with is this sine 2x. I don't have a sine 2x up here, so we need to do something with that. Okay, so that's my reasoning. You might be tempted to rewrite that this way, but then you lose the only cosine 2x you have. If I had a cosine squared 2x, you could keep one for that and then change one to try to get that, but we don't. Okay, now what's sine 2x? I don't have a sine 2x here, but I have stuff with x's, so it makes sense. Go from the double angle to the single angle. Sine of 2x is 2 sine x cosine x. And everything's being multiplied together. You don't distribute the 2. It's not 2 times 2 times 2 times sine times 2 times cosine, because it's not plus or minus, right? If you multiply things together, you use every number once. And so you can combine the 2 times the 2, so you get 4 sine x cosine 2x, and that's what we were trying to get to. So that one really is, it's a 3-step problem, and the last step is trivial. Now, what if we had started with the right-hand side, right? You'd have to realize, and this is reasonable to do, you have a sine x cosine x here, which is it looks like this, and you're missing the 2. So you probably might realize, break the 4 into 2 times 2. Steal a 2 from the 4 to use with that. And then that becomes that, and then this looks just like the right-hand side, and then you'd go to that side. So you could have started on the right-hand side just as easily. Okay, now the last example says, rewrite tan 3x in terms of tan x. Okay, so not just plain tan x, obviously. They want us to do something to this expression, tan 3x. And our final answer just needs to have a bunch of tan x's. They don't want the angle to be 3x anymore. They want the angle to be x. Right? So, for example, here, if they had said, rewrite sine 4x in terms of sine x and cosine x, I couldn't have stopped here, right? Again, I'm not referring to prove the identity. Okay, I'm making up a new problem here. What if they gave me sine 4x and had the same similar instructions? Rewrite sine 4x in terms of sine x and cosine x. There's a sine x, there's a cosine x. That's cosine 2x. You'd have to break that one down in terms of the single angles, okay? So here they don't want a 3x. They only want the angle x at the end. Now you could, okay, don't write this down because I'm going to erase it. You might say, well, I have a tan 3x. Let's break it down because it's in this section using the double angle formula, right? So if you did that, you'd have 2 tan of whatever angle's here, half of it goes here. So that would be 3x over 2 over 1 minus tan squared of 3x over 2. This is a true statement, but you've kind of made a mess of it because we're trying to get to tan x. We went from 3 to 3 halves, and we made it a mess. Okay, so you don't want to do that here. right? Because you got fractions to deal with then, okay? And how are you going to go from the fraction to x? If this had been tan 4x, sure. Go from 4x's to 2x's, and then 2x's, 2x's. That would have been okay. Right? Now what you want to do here is go back to the previous section and rewrite this as tan of x plus 2x. So break the 3x up into x plus 2x. Okay. Now I'm not using this formula, right? I'm using the formula from the previous section, the tan of a plus b formula. So this is tan of x plus tan of 2x over 1 minus tan of x, tan of 2x. That's your tangent of a plus b formula. Okay? And so notice we made a little bit of progress there because we do have a tan x in the problem, but we also have tangent of 2x. Right? And the problem said right in terms of tan x. So this tan x is fine, but the tan of 2x is not. So what do we need to do? Well, we know what tan of 2x is. Tan of 2x is this. Right? So tan of 2x is 2 tangent x over 1 minus tangent squared x over, okay, so I'm just replacing that with that. 1 minus tan x times tan of 2x, so it's that again. Okay, that's kind of a mess. We need to try to clean that up. Okay, well, let's use the idea, I'll leave this in there. Let's use the idea I mentioned in the previous video. We have fractions and fractions, right? I have a fraction and a fraction. I have a fraction and a fraction. You could get a common denominator and add, common denominator and subtract, then invert and multiply and try to simplify. What a mess, right? So I think the easier way, I say, right? Again, you can think of that as over 1, too, right? Look at all the denominators in the fraction. So I have a 1 minus tan squared x, a 1 minus tan squared x. What's the least common multiple of those? Well, it's 1 minus tan squared x. So if you want to wipe out all the fractions in one step, I'm rewriting what I already have there. I'm going to combine those. That's tangent times 2 tangent. That's x is 2 tangent squared x. Okay, so that's what I have. And remember what I told you to do to wipe out all the fractions in one step is multiply by the least common denominator over itself. Again, we have a 1 minus tan squared, a 1 and a 1 minus tan squared. So I'm going to multiply by 1 minus tangent squared x over itself. So if I've chosen the right expression, all the fractions in the fractions will wipe out. So let's distribute. So I have tan x times 1 minus tan squared x. Right? So tan x times 1 minus tan squared. So I have to distribute the tangent there. I get tan x minus tangent cubed x, right? It's that times that and that times that. And then this times this, the 1 minus tan squareds cancel. And I'm left with 2 tan x. And do the same thing down here. 1 times 1 minus tangent squared is 1 minus tangent squared x. And here the 1 minus tan squareds cancel. I'm just left with minus 2 tan squared x. And notice all the fractions and the fractions are gone. I know this one's a little more complicated than the one we did before because the least common denominator is kind of messy, but it works. And now combine like terms. I have a 2 tan x and a tan x. That's a 3 tan x minus tan cubed x over. And then I have a minus tan squared minus 2 tan squared is minus 3 tan squared x. And notice I've rewritten tan 3x in terms of tan x, tan x, tan x. And there might be other ways to approach this, right? Instead of doing the tan of x plus 2x, but that's the first thing that occurred to me. Okay, so there's probably lots of answers here, right? This isn't even. So my point is, if you do an odd problem like this and look at the answer at the back, you may not get the same thing they do. It's probably correct. They just may have approached it a different way and gotten a different answer. Okay. Okay, so that completes that section.